Sure, if you can do that. I just sent a text to him and to Aisha. Aisha did not have the invitation, but she does now. So, okay, well, uh, and I think they should join soon, I hope. But thank you, everybody. So I'm happy to present today. I hope everybody's doing well. I heard there was a little discussion of the weather. I can tell you that it's sunny here today, which is great. Um, and I'm happy to present today on energy sustainability, and I will talk about many things associated with energy, but I will also talk about generating energy from sunlight. I just added the date to these slides, so that's not going to be in the PDF, but I think we can keep track of the dates of the presentations separately. So for those who are new, I'm here at the University of Toledo. My name is Randy Ellingson. I'm a professor in the Physics and Astronomy department, and also I am also a faculty member of the Wright Center for Photovoltaics Innovation and Commercialization. The Wright brothers, W-R-I-G-H-T, were innovators in flight, and they are from Ohio, even though in the US the first flights were in North Carolina on the Outer Banks. So we received a grant from the state of Ohio to establish the Wright Center for Photovoltaics Innovation and Commercialization in about 2006, 2007 timeframe. I joined the university in 2008, and I currently hold the endowed chair, the PVIC endowed chair in photovoltaics. There's a logo here also for Glass City Community Solar. That is a local nonprofit that I helped to start, and is pretty active with students from the University of Toledo. And our mission is to serve with a focus on equity in the low-income community, to serve the local area through solar energy and related activities. So I will go ahead and get started here. This is a photovoltaic array in front of our primary research building for PVIC. It's the so-called R1 building. This array is just a little under 32,000 watts DC. And you can see, for the most part, you can see it has 4 different rows or 4 subarrays. The details of these arrays are listed here. And this is just kind of a preview to the kinds of technology that we're talking about. In this case, the azimuth angle is the projection onto, let's say, the 360-degree northeast, south, and west direction. The azimuth angle for this array is 180 degrees, so it faces south. And the tilt angle from perfectly flat is 35 degrees, so it's tilted to improve its collection of sunlight. Okay, so let's talk a little bit about energy. Okay, so probably the most famous energy equation for the masses of people is E equals mc squared. We're talking about that in one of my physics classes right now, but a more important equation is the equation that has to do with the energy of a photon. And in this case, in this form, it's Planck's constant times the speed of light divided by the wavelength. And from a physics, this was really a revolutionary idea that light is quantized into photons. And it also plays an important role in solar energy, where those photons that are absorbed by a photovoltaic cell each generate 1 electron. And for the most part, the collection of those electrons is quite efficient. So there's a pretty strong correlation between, very strong correlation between incident photon flux and the current that can be generated by a solar panel. Okay, so a photon is a quantum or a unit of light. It's a particle of light. Let's back up a little bit and talk more generally about energy, which, as all of you, I think, know, comes in many different forms, including, just starting in a random spot, sound energy. So the energy that you're hearing is generated by a speaker that is creating vibrational pressure waves in the air, and those pressure waves reach your eardrum, and through the magic of physiology in our brain, turns into something meaningful to us. Light energy we're very familiar with. That's also often referred to as radiant energy, and it is the primary form of energy coming from the sun, for example. And then there's kinetic energy, the energy of motion, which really, when you look on the atomic scale, is the essence of thermal energy. And then for objects in motion, mechanical energy, and even for some forms of electrical energy and magnetic energy. Potential energy is more along the lines of chemical or elastic energy, nuclear energy prior to its conversion, and gravitational energy. Of course, gravitational potential energy is a one that we well know. So when we're talking about energy and power, welcome, Tyler. I don't know, Tyler, if you want to turn off your camera, you can. So when we're talking about energy and power, there are standard international units for these measures. So for energy, it's the joule. And for power, it's the watt. And when you talk about everyday life, we're much more likely to be familiar with watts than we are with than the unit of joules. And so in everyday life, when you're talking about electrical energy, you're more likely to talk about kilowatt hours. So since energy is power times time, the kilowatt hour makes sense because it's a power in kilowatts times time in hours. If you can keep in mind some benchmarks for power, it'll start to be more meaningful to you, and you'll be able to evaluate what's reasonable and what's not. For example, a toaster or a toaster oven, when it is on and the elements are glowing, it's converting about 1,000 watts of electrical power into thermal power. So that's about 1,000 watts when it's running. Microwaves can be similar. They can be 800 watts or 1,500 watts. I refer to a 100-watt light bulb here, but that's really kind of quickly becoming obsolete. There are some people in the United States who, probably really prefer incandescent bulbs, but most people now are using LEDs after transitioning through compact fluorescent bulbs. There's some other references here for a dehumidifier. A cat generates about 5 watts of power when it's sleeping, and maybe 25 watts when it's up and around and playing. If I don't know what your electric bills look like, we'll take a look at one here, but you pay for the energy you use each month, and power is just the rate at which you're using the energy. Tyler, can you hear me? Okay, Tyler, if you want to turn off your camera, you can. There's a little button up there in the Teams. Okay, so global energy consumption. These data have not been updated for a little while, but in 2016, global energy consumption was 85% based on fossil fuels. So this is primary energy, and primary energy is the starting form of the energy which can be converted. For example, in an electrical power plant, you're going to be converting normally going to be converting some fuel, like coal, for example, into electricity. So you can see here the big ones are oil, gas, and coal, fossil fuels. Um, and that has a big implication for, this has been the case, except probably higher percentages even in the past, but this has been the case for, many decades to basically 100 years. Um, Here's some other data from 2016 that shows where our greenhouse gas emissions come from. Almost 75% was coming from energy use and energy generation and energy conversion in 2016, with other significant components directly from industry, the chemicals and cement industry, and from agriculture. Um, for anyone who may not be familiar with the details of the greenhouse effect, I'm sure that you've had a chance to walk into a greenhouse that's growing plants. That is a different type of effect that warms the greenhouse. In that case, the solar energy that enters the greenhouse and heats the plants and the ground and then also heats the air. That air is trapped, so it cannot mix convectively with the atmosphere. Therefore, because it's trapped, it'll warm up more and more. In our case, it's less about, it's not about trapping the air, it's about actually trapping the infrared radiation that cools the Earth as a whole. So there's some numbers on here, but there's a certain amount of solar radiation that is reflected off either the atmosphere itself or off the surface of the Earth, and reaches and is absorbed by the surface of the Earth or the things on the surface of the Earth. Subsequently, as we know from those of us who are familiar with black body radiation, everything radiates, including the Earth. And so the black body radiation that's leaving the Earth, then some of it is intercepted by gases in our atmosphere. So that's a normal natural effect. But as we change the mix of gases in our atmosphere and increase the concentration of carbon dioxide, we increase the amount of infrared radiation that is intercepted and re-radiated in all directions, including back down towards Earth. So it's a relatively small change in the balance of energy flow that is responsible for measurable changes to our global mean temperature and therefore climate and weather events as well. And so this is the basis for the greenhouse effect, which is really a big part of what we're talking about here, because climate change is something that's becoming, unfortunately more evident on a very short time scale. When it was first discussed in maybe, if you go back to 1990 and the year 2000, it always seemed like something that was far away. Now it's harder to think that's the case. So here's just a quick slide on the most important greenhouse gases. I mentioned carbon dioxide from fossil fuel and industrial processes. There's also carbon dioxide emissions from forestry and other land use activities. Methane and nitrous oxide are others that are significant. If you're not familiar with this, what we refer to as the Keeling curve, and again, I think that sometimes scientists and people have the tendency to learn about their recent history of science, kind of on a, not always on a global scale. So if I refer to work that was done here in the United States, this work was done in Hawaii in 1958. Now, Charles Keeling may not be the only person who was working on that, but from my understanding and from my perspective, he's the person to whom this measurement history is, attributed. So he started measuring. If you look at the lower right here in 1958, you see the red curves are the data measured at the Mauna Loa Observatory in Hawaii, and they're measuring parts per million of carbon dioxide as a function of the year. It's plotted here. And if you zoom in on this, I think there might be a zoom. So if you zoom in on it, you can see there's a little oscillation that's seasonal. And you zoom in on that, it turns out that this seasonal pattern is the carbon dioxide in the atmosphere is on a cycle that is in synchronization with the seasons, such that in the northern hemisphere, which it's the northern hemisphere that dominates the land and forested area of the globe of Earth. And so during the winter, when plant matter is decaying in the northern hemisphere, you'll see an increase in the carbon dioxide. And when there's uptake during the summer, you'll see a decrease because you are fixing carbon through photosynthetic processes. So that's the nature of this oscillation. And you can see, unfortunately, the big picture is that we are dramatically increasing our carbon dioxide concentration in the atmosphere. And if you just think in very simple mathematical terms, if you look at this graph here, you can see that the graph, not only are we increasing the CO2 concentration, but we're increasing that every year at a higher and higher rate. So the second derivative, if you will, is positive. And so the way I look at this problem, if you want to look at it mathematically, the first thing we need to do is to linearize this graph so that the rate at which we're adding CO2 to the atmosphere is steady and not increasing. Secondly, we need to turn that graph over so that it flattens out, so that the derivative is 0, so that it's flat. And ultimately, and this will take some time, we'll need to see the Earth start to recover and the natural systems start to reduce the carbon dioxide concentration in the atmosphere. Okay, just historically, if you go back using ice cores, for example, you can deduce the carbon dioxide concentration for at least back, more than 400,000 years. And you can see that we're already up here somewhere compared to where we have been over the last 400,000 years. We could pause for questions here, or we can continue. Ivana and Dragan, do you have any suggestions what you'd like to do?
I'm okay either way. So if there are no questions, we can continue. I don't have any questions.
Okay, I'll continue.
The same. Maybe you can finish and then they can ask.
Sounds good. Okay, so Earth has an estimated more than 7.85 billion people now. This is a cartoon from 2009 from a national newspaper, USA Today, and it's a climate summit you can see, and this person is talking about all of the benefits of taking care of our planet. And this guy stands up and says, what if it's a big hoax and we create a better world for nothing? And I think that the joke here is that all of these things are really important. And so, in effect, yes, it takes some cost and some thinking and some, coordination and collaboration, but the opportunities that we have to improve how we generate and use energy and water and how we treat our environment, there's only upside to that. Okay, so how much energy do we need? So from the US perspective, the average power, when you include everything, including transportation and factories and homes and schools, it's about 10 kilowatts. If you multiply that by the number of people on Earth, you get just about 80 terawatts. In 2017 or in 2019, the actual power consumed by Earth was about 19 terawatts. It's most certainly 20 terawatts by now or close to it. That's an average of about 2.4 kilowatts per person. So the US is consuming energy at a rate that's 4 times the global average. But when you think about what we are working towards, and that is a high standard of living for people everywhere, you can recognize that this 10 kilowatts is closer to where we are headed in terms of energy consumption than anticipating that the world will come down to an average much below 2.4 kilowatts, because energy is really important for health and for standard of living and so forth. So this is energy for electricity, and I just want to kind of start with let's start with the sun, but let's focus in these areas here. Fossil fuels were created over tens or hundreds of millions of years from biomass. And so there are a number of ways that you can generate heat. And one is burning fossil fuels. Another one is burning biofuels. Another one is through what's called concentrated solar power, which is really, the grand scale analogy to taking a magnifying glass and burning a piece of paper. You're concentrating the solar power to generate heat directly from the radiant energy. Geothermal and nuclear, they all generate heat. That heat then can be used to power a boiler, which in turn can be used to turn a turbine. That's kinetic energy. That kinetic energy then can be used with a generator, the way we and you in Serbia do it with a coal-fired power plant or natural gas-fired power plant, or a nuclear power plant, and you generate electricity from the electromotive force. So the sun also drives the weather, which drives really the ability to do hydropower and the ability to do wind power. And then, here we've got photovoltaics, which is really kind of an end around, if you will. So directly from sunlight, no moving parts. Typically, the photovoltaic panel can generate electricity. Okay, so how much energy do we need? So this is the global energy potential. These are terawatt years. Okay, so 900 for coal. Nuclear is maybe up to 300 terawatt years. Oil and natural gas are shown here, relatively comparable to each other. And then these are renewables, right, that are driven by, really driven by the sun. And so you can see here, wind maybe as high as 75 terawatts. Hydro, only 3 to 4 terawatts. And actually, I think we're using a good part of that already. Biomass, geothermal, waves, tide, relatively small. It's this big yellow sphere here that's solar that has a potential of 23,000 terawatts. So it dwarfs everything, and it's a constant source of power. So it's not measured in terawatt years unless you wanted to estimate how long the sun is going to live. And well, that's a long time and a huge number. So have at it. So this slide is called My Kind of Nuclear Energy. And so NIMBY means not in my backyard, which means if you're going to have nuclear energy, it's nice to have it far away. So in this case, we have a really nice fusion reactor that's the center of our solar system, that is the sun, radiant energy transferred to the earth, and then solar panels that can collect and convert that to electricity. So in a sense, by building these solar panels, you're taking the fusion reactor and making that energy accessible. So in this particular slide from Perovskite Solar Cell Company, they say this is the cheapest fusion reactor in the universe. So Okay, so if you look at how the radiant energy in sunlight is distributed, first of all, I'll just point out this gray curve right here that's smooth. That is the Planck's black body spectrum for about 5,250 degrees C. If you look at the sunlight at the top of the atmosphere, it's this yellow curve that is referred to technically as air mass 0 or AM0. It's also referred to as extraterrestrial irradiance. And you can see it does have some structure in it, and that has to do with the fact that the sun's outermost region is called the photosphere, and it does have a rich mix of elements, and those atoms each have absorption and emission lines that influence the shape of the spectrum. The red curve that's filled in here is the intensity of sunlight at sea level, and you can see this is as a function of wavelength here. This is the visible part of the spectrum where it peaks. There is energy in the ultraviolet, there's energy in the infrared, and it turns out that for most photovoltaic panels, which are made of, most photovoltaic panels are made out of crystalline silicon, and crystalline silicon has an absorption cutoff at about 1100 nanometers, and any photon that has energy greater than that can be absorbed. So that's this part of the spectrum right here. It's the majority of it. Other types of solar cells have different cutoff wavelengths for absorbing light. But if you look at these units here, it's power per unit area. So you can think about like a 1 square meter collector of sunlight, and then it's per nanometer. So that refers really to this axis, which tells you that, for example, at about 500 nanometers, you have a little less than 1.5 watts per square meter between 500 nanometers and 501 nanometers. And so if you add up all of the irradiance under this curve, you'll get 1,000 watts per square meter. So that's if this is the air mass 1.5 curve, AM 1.5. So it's about 1,000 watts per square meter of incident sunlight. If you look at the same data in units of photons per second, per square meter, per nanometer, these numbers are big. That's because photons don't carry a huge amount of energy one by one, and so there are a lot of photons. As it turns out, even if you calculate the photon flux of a laser pointer, it's high. So, okay, so the photovoltaic resource in the United States, it's distributed. The southwestern part of the country is the most intense. This is for a collector that's tilted at the latitude. So the collector would be tilted more if you're further north and a little less if you're further south. The Tropic of Cancer is still south of Florida even, so we're north of the Tropic of Cancer everywhere in the United States. But you can see here the intensity goes above 6 kilowatt hours per square meter per day. So that's solar, so sunshine, radiant energy on an average day, averaged over the course of the year. Toledo's right up here. We're down just a little over 4.1. And you probably know this, but maybe it's on the next slide, but we have more solar insolation, this word here, insolation, than Germany does, even in Toledo. So a brief introduction to a solar cell. I know that Ivana is going to cover this in detail soon, so I'm not going to spend too much time on this, but you can think about a solar cell like a battery. Anytime the sun is shining, it acts like a battery, so it can deliver current and voltage, and current times voltage is power, so it can provide power to an external electrical load, like a washing machine or a stereo system or a factory. And I'm not going to spend too much time on this either, but this is how we characterize solar cells in a way that allows us to share information across labs and across countries. We typically measure the current versus voltage for a solar cell, and when the light is turned on, you get power. So this MPP is the maximum power point. And we frequently also measure the quantum efficiency, which is defined here as the ratio of collected electrons to incident photons, and you can see it's as a function of wavelength. So if you look, for example, at the red curve is CIGS solar cell. It has a narrower band gap, so it can absorb all the way out to 1100 nanometers. This cadmium telluride solar cell shown in green absorbs only out to about 900 nanometers. So I'll keep going here. So, again, the history is from, I guess, my perspective, and there's more to learn, I'm sure, globally on what kind of work was happening in other places. But one place that solar energy research was happening in the 1950s was this Bell Labs. And so these are some this is an old advertisement from way back when. This is a photograph of a photovoltaic module as they looked in about 1979. These are silicon cells that are wired together, and the positioning has to go around the connections here. Solar cells were put on communication satellites as early as the early 1960s. Okay, so here's a demonstration of, here's me demonstrating solar energy. If I can get this video to work, let's see what happens here. I hope you'll be able to hear it. It's like nothing's happening so far. Let's see. I don't know. It's in the PDF file. Maybe I should bring the PDF file up.
I don't know, but in PDF file it's working. I tried today, so everything was fine.
All right, then we'll do it that way. See my screen? Just have to figure out where I am. Close. Full screen. View, full screen. Where's full screen? Yeah, there it is. I think it will start momentarily. Or not.
I think when you press the button, then you have to allow something. I had also problem today, but it started in one moment, so.
Yeah, I agree. It may be that it's not local on my computer, so it may take a moment because this is a large file, as you noticed. Okay, well, maybe I'll move this and we'll come back to that. Oh, I was on the, not sure what happened. see here. Just 1 second to do one thing here. Okay. Skip that. Go on to just a turn my camera back on. Oh, my camera is on. Okay. So this is a crystalline silicon solar panel. And each of these individual cells is a single crystal wafer. You can see there's a stack of them here, and these are going to be wired in series typically with one another, and so the voltage from each cell will add to the voltage of its neighbors. And the conversion efficiency for these is now greater than 20%, is available commercially from many different manufacturers. SunPower is just one of those. And you can see here it has an aluminum frame, and produces a power for this size, would produce a power of somewhere around 350 watts. Another technology that's important to us here at the University of Toledo is cadmium telluride photovoltaics. This particular panel shown here is about 0.6 meters by 1.2 meters. So in that's about 4 feet by 6 feet, for those of you familiar with those units. And the power conversion efficiency now for this technology is commercially is greater than 18% and close to 19% in some cases. Sorry, this is 2 feet by 4 feet. First Solar is now making larger panels that are about 4 feet by 6 feet. I think I can come back to this another time in the interest of time. So this is another video that you can watch on the PDF. It's really quite nice. It's unfortunate that it doesn't seem to want to play right now. I think that may have something to do with the fact that I don't have a copy of the file stored locally. It's on like Dropbox to save space, but let me see here. Maybe it is. Anyway, we'll come back to that another time. We'll get that working and share that next time.
Randy, maybe I can try to.
Sure.
To start your.
That would be great. You can just take over. You can just take over the screen sharing, if it works for you.
Yeah. I don't know. Can you see? Presenting.
Yeah.
Do you see?
Yeah.
You see. Okay.
Maybe you can go full screen. I don't hear anything.
You don't hear?
No, but you can hear it, right?
Yeah, I can hear.
I think we don't.
You still don't hear?
That's right.
Still nothing.
Still nothing. I assume others can't hear it either.
We can hear. No, cannot hear. No.
Cannot hear. Okay.
Even though. Shall I stop if you cannot hear?
Sure. I mean, yeah, I think so.
Okay.
But the other one I think doesn't have any narration, so the other one you could play, the first solar
Okay.
video.
Okay, because I really don't know why it hasn't sound.
So this shows the Series 6 manufacturing. And I can provide some narration here.
Sorry, I have a problem. Just a second.
Oh, I think I got it to work.
Mm-hmm.
Yeah, I've got it. I figured out what I needed to do. I needed to turn off the laser pointer, so I'll go ahead and show those.
Okay.
All right, so now, and let me know if you can hear it.
I cannot.
We can hear, Randy.
You can or cannot?
Cannot.
Cannot.
All right, let's see here. Ah, PC mic and speakers.
But okay, they can watch a video so you can explain, so it's not a problem.
Yeah. Okay. So this light is our simulated sunshine. This is a silicon mini module available on eBay. We've got leads coming off that can be plugged into either a multimeter or into a pump that I'll show you later. So there's the pump in a basin of water. So this multimeter makes it easy to measure things like the voltage and the current. So we're going to measure it on the 20-volt setting first. Just hooking up positive to positive and negative to negative. And what you'll see in the beginning is 2.8 volts, and that's with just the room lights. It'll drop a little bit when you shade it. Solar cells are very, very sensitive to light, and they'll show some voltage and some current, especially some voltage, even in very low light. Turning this lamp on, things will get very bright, and you'll see the solar panel operating more as it normally would in sunlight. So that's about 7.6 watts. But it turns out that sunlight heats up the solar panel. But we're going to look at the current first. So that's about 0.25 amps. And if you tip the panel to be more direct into the simulated light, you get up to about 0.5 amps. And it turns out that that light illumination is enough to heat up the solar panel. And so we can demonstrate what happens when a solar panel heats up. So we're just going to move it away from the light for a moment to let it cool down. We're going to switch to voltage because that's where you can see a pretty significant effect. So it's still at about 5 watts roughly. So we're going to put it in the light again, and you'll watch if you watch the voltage, you'll see that it will drop as the temperature of the solar panel heats up. And so it's a little hard to see there. 7.5, 7.4, 7.3, 7.28, 27. So now maybe it's approaching some temperature. So the point is that weather and sunlight even difference for how solar panels behave. So solar panels like bright sunshine, that much we could guess, but they also like cold weather. So to assume that solar panels will not work well in the winter, well, if you're up high in the mountains and you have a clear day and it's cold in the winter, you can get very good solar energy performance. So now we're gonna hook the solar panel up to this pump in the basin of the water, and you can see that the pump turns on from the solar energy. So you've got energy coming from the power plant, right? So that's already undergone a lot of energy conversion from coal or natural gas or wind or hydro. That electricity comes through the power cord to the light. It's radiant energy. It's converted then to electrical energy by the solar panel. And then the pump converts that electrical energy into mechanical energy, which imparts kinetic energy to the water that then is overtaken by gravity. It has gravitational potential energy at the top. And, you can see it fall back down under the influence of gravity. And in fact, you can hear the splashing and so forth. So there's also sound energy created by this demonstration, if you will. And the last form of energy typically is thermal energy. So all the energy that comes through that power cord ultimately turns into heat. A lot of it in the light, but also a little bit in the water, for example. Okay, so we'll go to the next demonstration, which is First Solar's manufacturing process. And again, you do not hear the audio, right?
No.
All that you're missing in the audio is music. Okay, we made it. Okay, can you hear me? Okay.
Yes. We can
Yes,
hear you.
yes.
All right,
everything.
so one of the things that we'll talk about in this class is, or in these lectures and in this group, is how we can model a solar array. And some of the things that go into that are the irradiance, which is the sunlight's intensity in watts per square meter, the spectrally resolved version of that, which is shown here, and then insolation, which is integrating that over some unit of time, whether it's an hour or a day or a week or a month. A couple of undergraduates originally built a monitoring system for the solar array that I showed on the second slide. And you can see here an example of data. Well, it's actually from quite a while ago, from 2014, but we're monitoring the array power, which here reached about 25,000 watts. We're monitoring the irradiance. That was a little less than 1,000 watts per square meter. We also monitor the air temperature and the back of the module temperature. And so we record these data along with another irradiance measurement as much as possible on roughly 1 second intervals. Don't need to show that. I can point out that the solar industry is growing so rapidly that every 2.5 to 3 years, a company has to double their manufacturing space just to keep up with the market. And so I'm going to keep going here. I'll mention there's another technology called perovskites that has received a lot of attention in research and development. And if problems with the technology stability can be overcome, it is likely to be commercialized and available for purchase as well. I'm going to go a little faster here. This is actually a really important part of this presentation, but it looks like we're almost out of time. So we may need to come back to this in the future. When you think about carbon intensity, you can calculate the carbon intensity for your electricity depending on what mix of technologies contribute to that. So in Ohio, for example, we do still have coal, we have natural gas, we have nuclear, and then a little bit of some other ones. But carbon intensity, you can also look at that in terms of just how much energy is required to run a home, and so that's what this addresses here. So this is a bill from this is an electric bill from spring or May of 2020, and what you see here is the kilowatt hours of electricity that were consumed in the month of April 2019 through April 2020, and the total is down here. The previous 12 months, it was 4,407 kilowatt hours. And this is for the home that my family and I live in. And so for one of our physics classes, we wanted to calculate, what is the total energy consumed by a building in terms of the kilowatt hours of electricity and the quantity of natural gas in hundreds of cubic feet. CCF stands for 100 cubic feet of gas. And so the TTM stands for trailing 12 months. That was our electrical consumption from the power plant. And this is our natural gas consumption, which we use for heat. And so with a little bit of math, so in terms of the electrical power, you just divide the total energy by the number of hours in the year, which is 8,760, and you come out with 0.503 kilowatts, or about 503 watts of average power averaged over a full year for electrical power. Now for natural gas, you need to be able to convert the CCF into its energy content units, and convert the BTUs then to joules. And if you divide that by the number of seconds in the year, you can get the watts average power equivalent, which turns out to be about 2,000. So our natural gas consumption is at a higher power rate than our electricity consumption. That's because we have winter here, and we consume natural gas to run our boiler. And so if you look at the total average power for our house, it's about 2.5 kilowatts. So that's about a quarter of the US energy or power footprint for one person. We have four people in this particular house. And so, yeah, so here's an equation for total average power. If you look at the cost, I'm going to skip ahead a little bit here, but if you look at the cost, our natural gas cost about $165 that year. Our electric costs were, let's see here, why? Oh, that's the total. So the costs for our electricity and gas are actually pretty similar to each other for the year, and they total up to about, I thought I just saw that. If you look at the cost per kilowatt hour for electricity, we're paying about 13.3 cents. And for the natural gas, it's about 3.8 cents. I don't know why. I don't know why this says 163, but so here's carbon intensity information. So it turns out that hydroelectric has a very low carbon intensity. Wind is also low. Nuclear is also low. Solar is above 40, so it's about 25 times better than coal and about 10 times better than natural gas. And the reason it's not zero is because it takes energy to make the solar modules and to maintain these systems. So, you know, in Ohio, where we live, the grid electricity carbon dioxide intensity is about 0.63 kilograms of CO2 equivalent per kilowatt hour of electricity. And for natural gas, the intensity is about 0.18 kilograms of CO2 per kilowatt hour equivalent. So the natural gas is better than the grid, actually. And you know, if you look at the scenario where we were to switch over entirely to electricity so that we could conceivably run just on electricity alone, that would require us to install a 16.5 kilowatt array, and plus either have, you know, efficient energy storage or efficient net metering where we were delivering that power to the grid and getting clean power back from the grid. So that would cost more than $40,000, and it would take up much more rooftop space than we have. So it's just something to think about in terms of what it will take to decarbonize. So I'm going to stop here because I want to leave time for discussion. So let me stop sharing my screen. I can share my screen again if there are questions about the slides. But please turn on your microphones so that you can tell us the kinds of things that you're thinking about and wondering about. So we want to hear from you.
Maybe I can ask two questions. You can hear me, right?
Yes.
Yeah, it's Nicola. So for that first slide of the greenhouse effect, when you showed like the light from the sun coming to Earth, it was one confusing data for me, like that because when you talk about standard irradiation, yeah, that one, we say that it's 1,000 watts per meter squared, and here it is like the total radiation from solar is only 300 watts per meter squared. So why is that difference here?
Yeah, that's a good question. So that's going to be averaged over day and night and averaged over all latitudes.
Oh yeah, I forgot about. Yeah, I thought it's just in the moment where the sun is coming,
Right.
so it's performing. Okay.
Good question. Yeah.
Mhm. And another one was when you showed that solar radiation spectra. So like the difference at the top of the atmosphere and the sea level. So I just thought, would it be useful if the solar power plants are built on high mountains because of that much higher intensity irradiance of higher energy light?
Yeah. So Nicola, that is definitely a measurable effect, and you can find you can find equations or a formula that will provide you with an estimate of how much more intense the sunlight is at altitude. The practical aspects of building solar arrays, for example, if you're building a big one, it's important that it's close to transmission lines. And then, of course, it's going to be easier to build in sort of a flat field than on a mountain. So I think that the economic benefits of practical aspects outweigh the increased power that you could get per unit area. But you are correct. That is a measurable effect. So if you do
But
happen
for
to
some
have
large cities at high altitudes, it could be useful to have near solar power plants.
Yeah, that's right. That's right. And if you look at Serbia, and well, let me start with this. If you look at Ohio and you look at how much solar resource we have, I don't have a map of Ohio handy, but from the southwest, which is close to the city of Cincinnati, to the northeast, which is close to the lake and famous for bad weather, there's about a 15% difference in the amount of solar energy received over the course of a year. If you look at the best part of Serbia and the worst part of Serbia, I think you'll see a pretty big change also from the best weather to the worst weather. So that's something we could look at. These are good questions, and I just want to remind all of you that we want all of you to become very familiar with solar energy and water sustainability issues. We want you to become experts, and that's a big part of our role is to try to help create these kinds of conversations that allow you to learn. So please participate with questions.
So Randy, I just want to add about Nicola's question. I think one of our ideas was also to visit Kopaonik Mountain and to do some estimates of potential solar radiation there and spectral irradiance. So this is
that would be great.
Along those lines. And just for Randy, since he doesn't know, that's actually now it's a city of 30,000 people during winter. So there is potential there, and I believe there are some solar panels already.
Yeah, that's great.
Unfortunately, most tourists stay on the top of the mountain instead of staying, at small towns, at the bottom of the mountain. So anyway, there is some potential there, and also at other mountains, on other mountains in Serbia. But that was a very good observation.
Thanks for the answers, and it was really, really interesting presentation.
Thank you. Who else has questions? Any question is okay. Any question is good.
Randy, I had a couple of questions.
Okay.
Or maybe Dragana, if someone of
Yeah,
The other
I was
participants, please ask the question, so don't hesitate.
yeah, I was waiting a few seconds. I would rather hear questions from others because I can see Randy, you know, often here, and I can ask him question in person. So if there are no questions from others, I just want to hear about your opinion on this efficiency of solar panels. Like for solar, you know, I think you mentioned up to 17%. I looked online, they said up to 18.6% or something like that.
Yeah.
So generally, how they estimate those? I understand what you know quantum efficiency in terms of, you know, generation of electrons will mean, but
Yeah.
where does data come from?
Yeah, that's a good question. So the information on solar panel efficiency comes from measurements of the current versus voltage curve, like I showed. Let's see here, where is it? Well, there's some here, but let me go back to where I was here. So so it comes from these current versus voltage curves, and they're measured under what's called standard test conditions. STC, standard test conditions. And standard test conditions refers to this air mass 1.5. So it's a particular spectral distribution of light. And the total intensity is 100 milliwatts per square centimeter, which happens to be 1,000 watts per square meter. And so the other standard test condition is that the solar panel is held at 25 degrees C. So that's standard test conditions for you know, terrestrial, like Earth-based photovoltaic solar cells or solar panels. And so because that's standardized, you'll know what you're getting, you know, what you expect to get out of a solar panel at those conditions. One thing I'll add is that if you have, for example, a silicon solar panel and a cadmium telluride solar panel, and they're both, you know, just as an example, let's say they're both 300 watts, and you put them out in the field and you let them perform, they will behave differently. They'll behave the same when they're close to AM 1.5 solar intensity, which is kind of the near the middle of the day at a latitude of like 42 degrees approximately. That's, you know, on a sunny day, that's about what you'll get. And you know, they'll behave similarly to each other if they're at the same temperature. So, but my point is that if you watch them for a full season, you'll actually get better performance in hotter, more humid conditions. You'll get better performance from the cadmium telluride than from the silicon. And when it's like cool and sunny or cold and sunny, the silicon panel will work a little bit better. So they do behave differently. Their properties are different depending on what the material is that's absorbing the light. So, okay.
Sounds good. Thank you.
You're welcome. Well, if there aren't more questions, I could perhaps finish presenting these slides, but please interrupt me if you have questions. I'm going to skip ahead to where I stopped. And, you know, we'll just take a look at how fast photovoltaics has been growing. So the average annual growth rate was 34% every year from 2010 to 2020. We had 125 gigawatts of new PV in 2020. And I can tell you that we're very close to a total of a terawatt, 1,000 megawatts. Sorry, 1,000 gigawatts. We're very close to 1,000 gigawatts of PV. Probably reach that next year during 2023. This is the logarithmic scale. This shows solar and wind. And the projection that solar will overtake wind in terms of total global capacity sometime right about now. And so that's happening. This shows future projections for where our renewable electricity generation will come from. And you can see that while wind is going to continue to grow, solar would become an increasingly important part of our renewable energy here in the United States. If you go back to this slide, I guess I'll just point out that two of the rows, the front two rows, closest to the road and furthest from this parking lot, furthest from this building, were installed in 2005, and they consist of 8.5% efficient panels. So now First Solar, 17 years later, is making 18.5% efficient modules. The ones installed in 2014 were about 12.5% efficient. So you can see the rate of increase. But First Solar is not going to be able to continue increasing efficiency arbitrarily because there are thermodynamic limits to what can be achieved. And although there are technologies that can reach about 50% efficiency, those will not be economically relevant to this kind of technology in a field like this. When those of you who are able to visit here, you might meet some of these other people here who are also professors in our Wright Center for PVIC. I just showed something that I guess I should be trying to push it so I can get in trouble. But if you look at, if you look at the University of Toledo's logo, our colors are blue and gold with these 3 gold leaves. And in my opinion, we should change the leaves to green. So I guess I just need to start doing that more. There's one major trend in research and development, and also now coming into commercial application, is bifacial solar modules that can work not only from the front, but also from light that's scattered off the ground. So these are called bifacial solar modules. That can contribute 5 to maybe 20% in some cases, probably more like 5 to 15% additional energy if you can collect that light from the back. Another significant trend in solar cells is tandem solar cells that uses 2 different materials. For example, you might hear something about cadmium telluride with silicon. It's not a perfect combination of materials, but it's something that I understand is being pursued commercially. So we might hear more news about that. And in that case, with tandem solar cells, some of the light is transmitted through the initial top solar cell, so that's generating power. And the longer wavelengths in the red and infrared can be transmitted through and generate power in the low band gap cells, so that's generating power. So you can generate power more efficiently if you're splitting the spectrum this way. So a little bit more on bifacial solar panels, a little bit more on tandem solar panels and some of the work that we've done here. This is a perovskite silicon. This is not our work, but work of collaborators. This is what you see when you zoom in and take a cross-sectional electron microscope image. You'll see thin film that has to do with the transparent conductor on the glass would be down here. You see another thin layer that's called a window layer. you see the cadmium telluride layer, and in this particular case, we've got an experimental material here that's contains copper and aluminum and oxygen. And one of the research problems that we're working on is trying to improve the back contact to cadmium telluride. And it turns out that if you look at a diagram of what's called the valence band and the conduction band across a cadmium telluride solar cell, the way they have been made conventionally, you have this like downward curve right here at this backside contact, and that's a problem for good performance. And so we're trying to resolve that. We're trying to change how that interface and how that contact behaves. And in fact, we have a significant project on that topic here at the University of Toledo. We're collaborating with other groups, including the National Renewable Energy Laboratory and Colorado State University and First Solar. So that problem is somewhat, in this case, it's specific to the cadmium telluride absorber. Silicon has its own challenges, but they've been solved more easily because crystalline silicon is a single crystal, and you can see in the cadmium telluride film there are numerous crystalline grains that are on the order of 1 micron in size. This is just a little bit of data from an experimental back contact that showed better performance. We can use back illumination now on this particular solar cell, so it starts to become a bifacial solar cell, but you can see that the efficiencies are still relatively low, but it's an improvement. So we're trying to learn as much as we can about how to really improve that and make bifacial cadmium telluride. There's some information here on how the electrical grid can be impacted by solar photovoltaics and how we can use the grid more intelligently. For example, conventionally, we have generation, we have transmission, and we have distribution to the consumers. Now we have energy, more types of energy sources that can be connected to the grid, even locally on buildings. We have electrical vehicle charging. The batteries in electrical vehicles could serve as energy storage. We have energy storage systems as well. And what starts to happen then is you think about ways that you can use the grid intelligently. And it turns out that if you make even like buildings smart, they can act to help balance the electrical availability on the grid, because if you've got PV and wind, you can use weather forecasting to predict how much energy you will have later, and you can kind of do pre-cooling in the summer or preheating in the winter to anticipate periods where you'll have less energy in the future. So you start to have smart electrical grid. In this case, there's a demonstration of how you can reduce this variability. So this is from a photovoltaic power plant right here. And this is a hardware software platform called Voltron that we use to work on smart grid projects. Halloween is coming up. Some of you have seen this slide before, but if you're looking for costume ideas, you could be the sun or a solar panel with an inverter. Not saying you should, but if you do, send us photos. Glass City Community is a nonprofit here in the Toledo area, trying to solar energy that benefits the LMI, stands for low and middle income community. We focus on the low income community, and we've been able to install a 47 kilowatt system on the rooftop of a building here in Toledo. These are some of our partners. This is the Department of Energy. And we're a nonprofit, so our funding comes from donations. I'm not asking you for donations, but if you have any wealthy friends and they want to help area solar for low-income people, then Glass City Community Solar would be a good place to put that money. This is another array that's owned by Glass City Community Solar. It's on a low-income apartment building that houses. There are 100 apartments. There are 288 solar panels on the roof. There are 6 inverters. It's a total 69 kilowatt capacity. Tilt angle is just 10 degrees. The azimuth angle faces south. And this is a calculation of how much energy that array would produce when it was new, for example. Solar panels do degrade very slightly at a very slow rate. So after 10 years, you'll have you expect to have some lower output, but this is an example of energy modeling using a software package that I will talk about later. So in conclusion, I think that our global society's challenges for sustainability are really focused on solving the climate change crisis. Photovoltaics provides the primary solution in terms of energy generation because it is so clean and so abundant, and costs continue to decline. So let's get things moving in Toledo. Let's get things moving in Serbia. Decarbonization does have upfront costs associated with it, but it sets us on a sustainable pathway at the same time. And persistence is needed across the board, not only in terms of research and development and material science, but also in terms of familiarizing people with the technology, improving policies, being smart about how we maintain and operate these systems, being smart about where we install them. And so, we do have the technology to make a huge dent in the global carbon emissions, but we need to continue to focus on these problems. And to some extent, it does take money, but to a larger extent, it just takes people. Okay, so acknowledgements for my funding at the university. Most importantly, I need to add the funding that's mentioned on the first slide, which is from the U.S. Department of State and through the U.S. Embassy in Serbia. That's not mentioned here, but I'm saying it verbally. We thank our sponsor for giving us this chance to create new energy ambassadors and energy and water experts. And so please, let's talk about that now. Okay, so now we're really out of time, but I hope someone at least has a question or two before you leave. And if not, then I'd like, go ahead, Ivana.
I would like to first, I would like to first of all thank you for the nice presentation, and especially the nice video from the first solar. And so you showed there the cadmium telluride solar cell. So how you make? So I'm interested in that, in how many % are present for the industrialization, that kind of type of solar cell.
You're wondering what is the % efficiency at the manufacturing scale?
Yeah, something like that.
Yeah, so I think that the highest efficiency modules that are made. So what happens when First Solar makes solar modules is they'll make them one after another, and each one is tested under standard test conditions. And then depending on the power output, which is directly related to the efficiency, they will put them into bins. They will categorize them as 350 watt, 360 watt. Actually, I think the ones they're making now are more like 425, 430, all the way up to maybe 460 watts. And I think the highest efficiencies correspond to, or sorry, the highest powers correspond to efficiencies over 19%.
Okay, that's really nice.
And I can tell you that I
And
had the
compare, for
opportunity.
example, to silicon, how much they are present on the market.
Yeah. Oh, how much they are present on the market. So
Yeah.
if you look at the global photovoltaic module market, I think my best estimate is that slightly greater than 90% is from silicon. Approximately 5% is from cadmium telluride, and the rest is other technologies. So it's maybe 5%, 90%, and but I can tell you that First Solar claims, and I believe that they have the lowest energy input and lowest cost manufacturing compared to silicon. They also have the lowest water impact, and they do have a pathway to higher efficiencies. I would say 22%, 23% in modules over the next, say, 5 years. And they do have plans to gain market share. One of the questions that exists for cadmium telluride is tellurium supply, because tellurium is not a material or an element that is mined intentionally. It's only recovered as a byproduct. So it's recovered as a byproduct from copper mining, for example. And so one of the things that they and the broader community are very interested in is how to increase the recovery of tellurium to both increase the supply, but also to keep the price low. So.
Okay, thank you very much for your answer.
Yeah, you're welcome.
With regards to that, Stratton here, with regards to that solar versus wind slide that you had in terms of development over time, the last couple of years on that slide were predictions. So if I'm not wrong, at least a couple of last years, because it's probably not slide from this year. I guess it was a couple of years back. If I'm not mistaken.
I can get back to it, I'm pretty sure, very quickly.
Yeah, well.
Here.
Okay, so forecast was from 2018 on. It would be very interesting if it would be possible to get the actual data in these last 3 or 4 years.
Yes,
first, it
I
would
agree.
be interesting in itself, and also because both technologies are developing, and it would be very nice to see how much that affects those extrapolations. So I don't know if that's readily available data or not, but
yeah, I'll just say, Stretton, right, that
yes.
Every time, so my main responsibilities are still material science research, but I do frequently give talks like this, and every time I go to give a talk, I want to update these slides, but I don't always have time. And it's always a bit of a challenge to find the data from the most recent years, but in this case, I think we can find this. And so do you want me to do that, or do you want me to assign that as homework to everybody else?
Well, we can try either. So
okay.
Everyone, or good afternoon.
Hello. Yeah. So I think those data are out there. This is global cumulative installations. I mean, it probably would not bring my web browser up and search right now, but I'll see what I can find and share it with the group, or if someone else finds something interesting, you can share it with the group. I would like, let me ask a question about Serbia. If you found a news story from within Serbia about a solar installation, for example, would it ever be in English, or would it only be available in Serbian?
How you mean, Randy, if we found?
I mean,
any
how common is English in Serbia?
Very common.
What about in
Randy,
Almost all, at least younger generation. I mean, younger. I mean, from 40 and younger, they speak English very well.
Okay, what about in print? If there was a newspaper
Yeah,
in Serbia,
so, Randy,
it would not be in English, right?
they're news
Newspaper is
outlets.
difficult. Yeah.
They're like websites, you know, that have English translation, but
Yeah.
not all of them. So
If someone could send me a story with a photo about, or send all of us a story with a photo about a solar system in Serbia, I'd be interested to read about that. And I'd like to learn more about what, you know, if you talk to people about solar in Serbia, what are their thoughts? What do they think about it?
sounds good.
Yeah.
Yeah.
Other
Okay.
comments and questions? Mulatin or Sanita or Sretan, or actually, I just talked to Sretan. Katerina?
I'm good. I had many questions, but while you had a presentation, you answered everything I had in mind and in questions. So thank you.
Okay, thank you. Okay, Dragon, what do you think?
I think this was great. Thank you very much for taking your time of your busy schedule. I think it's certainly a big responsibility.